story of true color holography begins in the 19th century with this gentleman, Gabriel Lippmann, who in 1891 proposed a new method of making true color photographs, which gained him the Nobel Prize in 1908. His idea was to focus the image of an object onto a photographic plate, but the emulsion of the photographic plate was not pointed towards the lens, but in contact with a pool of mercury. The reflection of the image bounced back onto the incoming image light, and it formed an interference pattern. Interference patterns are formed with light when the crests and troughs of two waves coincide. Sometimes there is constructive interference, making bright areas. Sometimes there is destructive interference, making dim areas. Depending upon the wavelength of light, the interference pattern will have different spacing. For the green light coming from the leaves of the flower, the fringes will be very closely packed because green light has a shorter wavelength than the red light that is coming from the petals of the rose. The amazing thing about these interference patterns is that, properly processed, they are capable of reflecting the color that formed them. In this way, he made true color photographs using no dyes or pigments. This is a cross-section of one of these Lippmann-style plates, showing the photographic deposit of the interference pattern. This is a holder for putting a photographic plate in contact with the pool of mercury. Not only did these early experimenters want to make views from life, but also to photograph the spectrum of different types of light. Here we can see one of these experiments. There were many people working in the 19th century and the early 20th century on making Lippmann photographs. The apparatus, shown here in a display in a museum, is very clever to hold the photographic plate in contact with the pool of mercury. Up above is the fruits of one of these pieces of equipment's handiwork, a photograph in true color of a stuffed parrot. There were many people who experimented with this process, and they gave us very beautiful views. Here is a view of Versailles taken by Lippmann himself. Notice the white of the building, the blue of the sky, the green of the foliage, and the red of the flowers. Many of these workers were in France, Germany, and the United States. Neuhaus, Valenta, Lehmann, and Ives. They all persevered in spite of the many difficulties, because they had to coat their own plates with an emulsion whose silver halide grains were much smaller than a wavelength of light. This meant that their exposures were very, very, very long, even in bright daylight, and by the time of the 1920s, almost all interest had disappeared in this type of photography, with the invention of much more sophisticated processes. The story continues with Professor Yuri Denisyuk of St. Petersburg, Russia, who in 1958 wrote a paper which proposed how to reconstruct the object's wavefront in 3 dimensions thanks to interference effects. Here is a 3-dimensional reconstruction of Professor Denisyuk himself, taken with a pulsed ruby laser. The Denisyuk scheme utilizes a highly coherent source of light, the laser, which takes the tiny beam and passes it through a shutter to time the exposure. A spatial filter expands the beam. The expanded beam passes through a holographic plate and then bounces off of an object. When the reflected object light meets up with the incoming reference beam, an interference pattern is formed. This interference pattern takes on the object's wavefront shape and then is capable of reproducing that object's wavefront, plus relying on the Lippmann effect, where the color of the recording source is also preserved. The Denisyuk process can also be used to reconstruct an object's wavefront in true colors if laser light is used of the additive primaries, red, green, and blue. In this example, a krypton and argon ion lasers are used to pass through the holographic plate and bathe the object in natural colored looking laser light. The holographic plate, if it can see all these three colors, can record the interference patterns and then conjure up an image of that object. Here is a CIE chart showing the possibilities of using three different colored laser lights to reproduce the gamut of the objects that we see in everyday life. For this experiment, 633 of Heaney, 488 of argon, and 532 of frequency double neodymium YAG were used. Other workers have suggested using different combinations of laser wavelength primaries. This is the work of Dr. Kubota in Japan. This is a special layer that he coated himself, dichromated gelatin. This is a combination of dichromated gelatin and the usual silver halide recording materials available commercially. The dichromated gelatin material, however, requires thousands of times more photons than the typical commercial silver halide plate, requiring great care in exposing and processing. The Russians make their own special holographic recording materials, of which this is a small sample. Dr. Bjelkhagen was fortunate enough to work with rails.
Laboratory at the Louis Pasteur University in Strasbourg, where we are doing the final recording of our color hologram from the color project that we have been working on. And we are working with a specially made color emulsion, single layer silver halide material produced in Moscow, and I am working together with Dr. Sobolev, who provided me with a lot of this material for our project here. And we are going now to take you through a little of the steps, how such a hologram is recorded, as well as we will show the results in on the video with the true color registration that has been possible now to record here. And you can see for yourself how good this is. We have both test targets, color test targets, as well as special color, suitable color objects that have been recorded.
There were two objects to be placed in front of the red, green, and blue lasers. This analytical one includes a CIE chromaticity chart, white and black patches to show the signal-to-noise ratio, and a shiny multicolored object to prepare for recording of a much more beautiful object. This is in preparation for the holography. We need to make some Lippmann photographs to check the response of the recording material to all the different colors of light. You can see that the mercury is being poured into the plate holder. The holographic emulsion is in contact with the mercury so that there is a very good reflecting surface right behind the light-sensitive coating. A slide of the analytical object had been prepared, and it will be projected onto this photographic plate so that the response of the material can be noted to see how well it performs in reproducing all the colors of the rainbow. These results were under a tremendous amount of time pressure, and so the results of the Lippmann photograph were not as perfect as those the experimenters of the early part of this century. The slide projector is turned on, light reaches the photographic emulsion, and here is the result. The most important part of the true color holography experiments are the lasers. As we pan across, you can see the helium neon laser, the source of the red, come into view. We'll take a look at its output end, and in the background we will see the argon laser in the back, the big white box, a blue helium cadmium laser in front of it, in the black box. The most important part of this experiment was this special frequency double neodymium YAG laser. A small infrared diode pumps a YAG rod, and then that light passes into a frequency doubling crystal to give out an awful lot of very, very nice pure green light, which is checked by a scanning Fabry-Perot interferometer.
By using laser diode pumped and frequency doubled CW neodymium YAG laser. The coherence length of 25 meters is a common feature of this laser that is, of course, extremely convenient for holography. To demonstrate the stability and the coherence properties of these lasers, the laser line is displayed by the scanning spectrum analyzer on the scope.
Now we are ready to expose the true color hologram. The lasers are all warmed up and ready to go. First thing we have to do is to find out how much red, green, and blue light is incident on the object plane. So we have a nice power meter in position to measure how much light is reaching from the red laser. It's very crucial to know how much light is hitting the holographic plate, because the exposure is what determines what the final color balance of the hologram will be. After the red reading is taken, the green beam is moved into position, and so now the laser is hitting the power meter detector. The detector has to be tuned in to the proper laser wavelength, and then we can find out what is the incident flux. From this figure, the exposure time for the green can be figured. Now the blue laser light is hitting the same power meter. Tune in the power meter to the proper wavelength. Now the exposure for the blue can be calculated and set on the shutter controller. The holographic plate is put into position under safe light illumination. The system is further isolated with styrofoam. Now we are ready for the first exposure, which will be blue. After the blue exposure, its mirror is moved out of the way. The predetermined exposure for the green is set on the shutter controller. The green light exposes the plate. The green mirror is moved out of the way. Now red laser light is ready to go to the target area. The shutter timing is changed. The red exposure is made. The plate is then removed for processing. Crucial to the processing for this experiment is a pre-hardening step. This eliminates shrinkage. After the proper amount of time in the pre-hardener, then the plate is developed. The pre-hardener is rinsed off, and the plate is put into the special color holography developer. The developer makes the plate turn dark, but after the developing step, there is another processing chemical called the bleach, which makes the plate crystal clear, like a piece of glass. This is critical because there cannot be any color filtering effect. While this plate is processing and drying, the system is realigned to make an exposure of the other object for this experiment. Here is the hologram and its completed state of the analytical object. It looks identical to the original. Every color is visible on the chromaticity chart. The white areas are nice and white. The rainbow-colored computer ribbon shows the full spectrum. The elephant is nice and shiny and multicolored. All regions of the CIE chart are described, and especially the white is as pure as the original. The two yellow dots are very good. This is an important part of color holography. Yellow is the hardest color to generate. Thanks to the 532 nanometer of the frequency doubled YAG, yellow recording becomes a snap. Now we will expose the other object. Now here are the results, and this looks just as good as the original. Another object that was holographed in this experiment was a small piece of jewelry with a lot of highly reflective specular surfaces. Here is the final hologram, and you can see all the little highlights and all their different little colors on the final hologram, just like the original. Part of this project was to look at the advantages of holographic recording for very valuable museum pieces. This small cuneiform tablet, although not very brilliant in color, has a lot of very small details which are exquisitely recorded by the true color holographic process. The most ambitious part of this holographic project was the recording of this porcelain Buddha. It's covered with a lot of pastel glazes, and it's a rather large object. The final hologram will be approximately 20 by 25 centimeters. The object is laid upside down in the holographic setup so that the plate can be laid directly on top of it for purposes of stability and preserving the overhead reference beam. Because this object is a lot larger, the exposure times need to be remeasured and recalibrated because the beam is spread out so much larger. Special stabilizing rods are added to the holographic plate so that it does not distort during the exposure time. Okay, the Buddha now is reproduced holographically. The pastel colors are all there. The advantage of this type of hologram is that it has an incredibly wide viewing angle. It is almost like looking at the object underneath a piece of glass. No matter from which angle of field of view you look at this, it's just as if the object were still there, even at these very oblique angles.
We have now seen a little how we make these type of holograms here, and we hope in the future to be able to further increase the quality of these holograms, as well as making larger format color holograms. We believe that this type of material, the silver halide experimental panchromatic emulsion that we have been working with and was produced by the Slavish company outside Moscow, is very useful for these type of recordings. In particular, as it will allow us for rather large format color holograms, which is not so easy with other materials like, for example, dichromatic gelatin or photopolymer material, because of the lower sensitivity of these other materials. We also hope that this will open some new possibility for display holography to be used in museums, advertising and so forth, when we actually can record the objects exactly the way they look, not only the three-dimensional shape that has been the possibility before, but now also with, which is even more important, the true colors of these objects. And therefore, finally, I would like to mention what is going on in Moscow for the moment, and Dr. Sobolev's project in Kremlin to try to record color holograms of unique art pieces they have in their collection.
This is Dr. Sobolev in front of his lab in Moscow. For this project, though, he is working at a different location. This is his lab, and he is setting up to make a hologram using a beam coming from above, because many of these objects that he has to holograph are so fragile they can't be glued to anything, and they have to be laid on their backs. This is the lab space that he is working out of in the Kremlin. This is the building, and inside the building, on the ground floor, is his laboratory. Here is Dr. Sobolev, his wife, and the director of the Kremlin Museum in front of the laboratory door. These are some of the objects that need to be holographed. This is an Easter egg called the Moscow Kremlin, from the workmen of Fabergé, somewhere around 1904 to 1906. This is another Easter egg. This is called Pamyat Azova, a small boat. Over 100 years ago, 1891 was when this was made. This is called the Flower, Cupid's Delight. It's got 5 miniature paintings of the Tsar's children in the flowers. It was made for the 10th anniversary of the wedding of Nicholas II and the Empress Alexandra. This is another Easter egg with the yacht Standard in it. A small gravy boat, 1899. And a cigar case from the last century. Here is a brochure from the company outside of Moscow named Slavish, which is the manufacturer of the holographic plates. These types of plates require the most exacting standards in their production. This is a newly published book by Springer Verlag that has a lot of insights into the processing of these plates, which is also key to the production of true color holograms.